Hello, everyone, and yeah, thanks for joining the deep dive. So the topic of today's deep dive is how to leverage simulation data, actual high-quality simulation data for AI-accelerated design and engineering. And just as an introduction, I want to show you what this is all about. At the end, the idea is that you leverage those data, the information that is included in this data, stored in an AI model, so that you can do the following. Let's assume you have like a design state in Alias, and you wonder what's the performance for this particular design. And usually you need to like export the geometry, give it to your colleagues in engineering. They need to do some model preparation to make everything watertight, then run a high fidelity CFD simulation if they want aerodynamic performance. This takes, I don't know, let's say 8 hours, at least 8 hours on high performance cluster system, and then you get some results back. And we hear from our customers that this process takes like between 2 days and also 2 weeks. And if you use the AI model to perform a prediction, then in Alias you have those results almost in real time. So this takes about a few seconds, and you can predict those results using the freshly released NAVDesign plugin, which give you like certain information. For example, which model do I want to load? Also, like, don't mess up the different units people like to use. Then you have an indication whether you can trust the prediction or not. This is like this confidence indicator here. You can also compute a frontal area if you like, because there's always this discussion about, is this like the higher drag, is this like due to a larger frontal area, or is it really like an aerodynamic effect? That's also something you can simply compute in the plugin, and then you get like, yeah, I would call them key performance indicators, something like the drag, lift on the front axis, lift on the rear axis, and also some field variables like pressure, wall shear stress, something like this. What comes naturally if you evaluate such a model is also what we call a sensitivity. So you basically perform a backward pass through your network, sum up all the gradients, and then for each control point describing the surface, you also get a sensitivity. It's like a heat map. Which areas affect a certain variable like the drag the most, and you also can get some information if you don't visualize the magnitude. If you visualize maybe the x component, y component, z component, since this is a vector, you can also get some information about where to push and where to pull to reduce drag or increase drag. This is something that comes natural, and this is kind of the end goal. And this talk is really about what's necessary, what are the right questions you need to ask yourself to make this happen, to train those AI models. Because if we think about what's behind this technology, it's really the task to train your own custom models. Because if you use your own data, your own simulation data, this is validated by your engineering department. This is something where you can really rely on, how to make decisions based on those kinds of data. And it's always like a hard task to provide something like a foundation model for automotive aerodynamics, because if you would give the same geometry to different OEMs, you probably would get a whole lot like different results. So the technology is really meant to run on site at the customers so that they can use their data to train their AI models. And once those models are fully trained, you can use them and feed your designs, your inputs, and your boundary conditions into the model and get those fast results, even on a laptop, instead of having to wait for like several hours or even days for results. So, and then if you can do something like this, I think you have lots of possibilities. You can easily adjust your design according to the results and evaluate again. So it's like a possibility for a lot of iterations. And yeah, you can imagine this. It's like this, that you just like evaluate design after design, get immediate results. This is just a visualization of this iterative process. And I think the nice thing is if you want to accelerate your design process, that this technology really works within Alias. And also now with the live referencing, you can directly use the result of those optimization loops to make like, you do use thread rendering in Alias. So this like captures a lot of spots in the design cycle, which is personally, for me, really a win-win situation. So, but let's move a bit more into the details. This is why I switched like from a black scheme to a white scheme and really start a bit the deep dive. And first item I want to address is a bit the tech history, because technology like this, it does not like pop out of the skies. It's really like, it has been years of work to refine this technology, really make it useful with high fidelity data, production-like data. So this is something I want to address and give you a brief overview of how this technology evolved over the years. Then I talk about data preparation. Since this is a data-driven method, it's all about data. It's all about data, inputs, outputs, distribution. There's some questions you need to ask yourself in terms of preparation. I give you also like an overview how a workflow would look like. What stages do you need to run through to create your model that you then can deploy? For example, in Alias, what other possibilities do you have? We can show like how the usage in Alias really is. And last but not least, talk about using this in combination with generative AI. So first item, tech history. So we started working on this topic 10 years ago, and 10 years ago, people used to call this machine learning. All the AI-related buzzwords, they did not exist at this time when we started. And at least for myself, I'm an engineer. I did my PhD in the wind tunnel, then did a lot of work on CFD, method development, actually running those simulations, improving the quality and the accuracy, and then switched to optimization problems and more to machine learning before I joined Autodesk. And 10 years ago, every problem, at least for me, looked a bit like this. So when people wanted to design or somehow they designed like an active rear spoiler. This is just an example we did at Navasto at the time. They kind of had a parametric problem. So they said, what's my design space? Design space needs to be described by certain parameters like the X translation of the spoiler, the height of the spoiler, angle of the spoiler, and maybe also some other combinations like you see here on the rear diffuser on the bottom, which is like, it also has like a large impact on the flow around the rear of the car. And what you then did is that you run simulations that capture those design space, describe it, be as smart as possible in terms of sampling strategies. And then first step was we really created a machine learning model at the time that had where's my mouse? Those parameters as an input. So those parameters were translated into those sliders. And now I start the live screen recording. So you change the parameter combination by moving the sliders, and you see that the resulting geometry is changing, the resulting flow field is changing, and also what is also changing are these scalar values like the drag, lift front axis, lift rear axis. And this was actually really a major step forward. So it enables what we call interactive design. So the vision was always design department, an engineering department, they move more together, they can work interactively, they see what's the impact of a design change and which areas are worth fighting for. So that's the idea, but we saw that when you limit the technology to those parameters, you run into certain problems. And then, let's say roughly 5 years ago, things happened where the people said like, I have this one project where I optimized the rear spoiler of my car. This is what you saw. It went smoothly. It was okay. But now I have another project where I need to optimize basically everything else on the car. But this car is maybe not the sports variant of this sedan, so it does not even have a rear spoiler. And then, but I have data for such an action, and I want to use it. I don't want to be limited to like this 4 parameters. And thinking of it, there is a next project which is also a sedan, but completely different level of, this is like really a production car. It has an exhaust system, not a smooth underbody, an engine bay flow. So it's completely different to like this research vehicle, the driver you saw in the first project. But people wanted to leverage all that data because they said like, we ran all those simulations. There's a lot of information. So basically, if we want to optimize the next sedan, we did the work already. The information is there, and then now I want to have like an interactive tool that enables me to perform this interactive design stages, but not limited to 4 parameters. And this is where we really said like 5 years ago, we switch gears a bit and really move to deep learning. So this was the stage where we really moved to AI, and the input is not longer a parameter combination. At this time, we really went to switch to geometries as an input, and I mean there are different models outside which you can use. It's like a CNN, convolutional neural network, basically, which is also quite likely used for learning images, point cloud transformers. But what we like to use most is the last 3-letter acronym, is a so-called GNN, a graph neural network. This is where we saw that this has the largest potential. It's very flexible. It gives you very accurate predictions. You can adapt it to lots of fields of application. So this is where we went through. And when you have the geometries as an input, you can do what I would call like the end result. You can really work in Alias, and whenever you designed like a nice geometry, either with wheels or without wheels, you can open the plugin, load a model, mark everything you want to take into account for the prediction, run a prediction, get it fast. Maybe do some minor post-processing steps, adjust the color bar, because I know from my own experience there are some personal preferences. But then comes the important part. You can adapt to what you saw, you can try to make it better, run the next iteration step, and really operate on all your CVs as you see fit. I mean, you can also apply something like a lattice box morphing, sorry for that. You are basically free. You can apply larger changes. You can also apply like smaller changes if you want. And at the end, if you're satisfied with your work and you want to see what's the delta, what's the next drag coefficient, you just mark everything you want to take into account, run the next prediction, and move on with this information. I think that's the idea. This works on subdivs, on NURBS, also works on meshes. I think when we talk about tech history, we may need to mention when we started, we used to really work on engineering meshes, let's say 200,000 points, describing in a tessellated mesh the geometry, and use either like direct manipulation of the surfaces, for example in Blender or in ANSA, could be any tool. You can also apply like those, as I said, the box morphing if you want. Just create the next geometry, hit the predict button, and use it. Use the information that is already available in your company that really like uses best practice from the engineering teams. So this knowledge is kind of condensed into the AI model, and then you can simply leverage it to predict those scalar values like a drag, a lift. You can also predict surface fields, pressure, washer stress, temperature, whatsoever. And you also can do some volume predictions. I prefer volume predictions on slices because that's what I look at the end. I don't like those streamlined pictures. As an engineer, it's hard for me to really like get some information out of it. Right. So if we want to train this model, as I said, it's really a data-driven method. So I need to have some initial thoughts. There are some important questions I need to ask myself. And the first question is always, which data is available? Because it's a purely data-driven method. The information that we leverage needs to be in that data. And the question is the database sufficient for my use case? For example, if I just want to work on the roof height of the car, it's just, I don't know, roof height higher, a bit lower, then it's easy to come away with, let's say, I don't know, 5 or 10 data points. I train an easy model, a super small network, and I can interpolate between all those heights. If I have more sophisticated changes, like on a full production car, even a Formula One car, then obviously I need more data to really like tweak small areas of the car and have more refined changes. That's quite important. The next very important question is, who is the end user? Is it like a model that is really like made for engineering to help with optimization steps, accelerate them, do some design space exploration as an engineer, because engineers use like slightly other data representations. I think no engineer really works like with subds and NURBS or like blended surfaces. It's mostly like a mesh that they are using. While the designers, you know this probably better than myself, they have like completely different inputs. And it's important, and I will come to this a bit more in detail, that you teach the network those kind of inputs. The network needs to know, do I have like watertight surfaces, or are those surfaces like completely disentangled from each other? I have gaps and overlaps and intersections. So this is quite important, but you can teach different kinds of input to the model. And we always get the question, yeah, do these models need to be watertight, or these input geometries? And the answer is no. No. If you teach the network to work on not watertight geometries, then it's working, run out of the box. And if you are about to run an optimization, it's always something to consider, because we are not operating on parameters. So how do you run an optimization without parameters? This is something I address at the end of my talk, but it's important to think about this. Right. So usually what we see is that when we want to answer the first question, which data is available, we see that there are two possibilities. One is that we just have data from engineering, and engineering only. And we need to kind of get additional design studio data to teach the network like both representations. Best case scenario is both teams really work together, and we have like basically two data streams, because at the end what we want to do to teach the network those different representations is that we map each simulation result or experimental result onto those two inputs. That's quite important. And since we are well aware that like in real life it's not that easy, because it's not the situation that you have both geometries available for each simulation run. It's simply not the case. I never saw this, but we deliver some small tools that can help you with this. And I think this applies for all machine learning actions, that if you use a software that helps you to train AI models, only maybe 5 or 10% of the software is really about deep learning techniques, different AI models. Almost, I would say, more than 90% is really like small helper functions that enable you to map results on different inputs, read different data types, do some data preparation, some tweaking. So smaller tools, and this is also like a smaller tool, because usually it's like we have a simulation, let's say a baseline geometry, which is simulation like watertight. You can feed it into star CCM+, OpenFOAM, PowerFlow, whatsoever. And you also have different variants. So maybe not just one variant, 100, 1,000 in Formula One, but you have like a transfer function. So the change from the baseline to the simulation variant, this can also be applied to, I just call it design baseline. It's just like an alias model. So what we do is that we really transfer this geometry change that we saw with the watertight meshes to the design meshes. and apply like a different machine learning model-driven morphing approach to this transfer function to also have the same variant, but based on an alias model. I think this is the trick. And then you put this in a loop and make it like a parallel workflow, and it's quite quick. And then you have like basically 2 data streams. You could also have like a third data stream. We had this discussion with some customers where you use, for example, like the scan of a clay model, which is like a different mesh again, and just add it and apply like the same workflow to it. Right. Speaking of a workflow, we observed one thing, and that is, since our customers are mostly automotive OEMs, they have very sophisticated processes in place. And those processes, they really took decades and millions of euros or dollars to be really validated and produce valuable, high-quality outputs. So these, we cannot easily say like, okay, now we have like we were a startup like 10 years ago. Please change all your processes, go to our platform and work there. I think this would have never happened. This would have taken like the next 10 years or 20 years to be really validated and performant. So this is where we said like our product is really an API. It's a Python API, so basically a library that stores all the functionality that you need to read in real-world data, large data sets, different data formats, pre-process them in a way so that you can train an AI model on it and that they also fit on a GPU. I think that's important. Then train those models, do a hyperparameter optimization to optimize those AI models, and also enable functionality so that you can predict in a way that it really helps you in your daily design process or development process. And when you have such a library, an API solution, it's all about creating workflows, combining those different functionalities or building blocks into something that does the job. And easiest way is just to derive Python workflows. This is the most flexible way, but we are well aware that some people don't like Python. So this is why we also said, like, you can also store those workflows in browser apps if you want this. And you can use the first 2 versions for pre-processing, for training, and also to run predictions. But I think the approach, like integrating this technology, using custom plugins into Alias, into Blender, into ParaView, into Ansa, something that people really work on a daily basis. I think this is the most powerful approach because you can really work interactively. You create a new design, you evaluate the performance, you say like, okay, I see like maybe it needs to go in that direction, and then you can follow this direction with some confidence and with some insights into actual results. I think this is quite helpful. And either way, you can use Python workflows, the browser plugins in the web browser, or the plugins. It's all about 3 steps. First step is the pre-processing. Second step is the model training. Last step, when the model is ready, is the inference. And in the pre-processing is really about collecting all the inputs and outputs. And with the engineering data sets, the inputs and outputs are usually encoded in a mesh describing the geometry. Then you have all the results in the volume, on the surfaces, in some CSV files, text files, like the scalar values, like the drag or the lift. This is what I would call metadata. Can be the outputs, like the drag, can also be inputs, like a fan speed, inlet velocity, ambient temperature, whatsoever. So this is something you need to collect, and since this raw data is huge, external aerodynamics is something about like 60 gigabytes usually per case. So if you have 1,000 cases or even more, then we are speaking really about large data sets. So this is why we said like, okay, the pre-processing should be like a single workflow. It should be flexible, and the best case scenario is that this workflow runs at this machine or at this place where also the raw data is stored, because like copying or transferring those large data sets is really a nightmare. Trust me, we tried, and it's not easy. So we usually do the pre-processing, and we save it what we call as a snapshot. It's like a binary data format. It has like VTK in the back end, so it's like exchangeable. It's an open data format, but I would say it's very efficient to store these kind of results. And this is something you can transfer either to a local workstation, to a laptop, GPU cluster, whatever, to use it in the next step, the model training, which is quite forward. It's like always streamlined. It's always the same. Train the model, optimize the losses, optimize the hyperparameters, and should save it. And for inference, you have like plenty of options. Since the prediction is really a 3D object, you can say like, when I do the prediction, I have the 3D object in my memory, and I can do it to do some in-memory operations. For example, create a PDF plot report, create some automated pictures, images, send them to the user via email that requested those predictions, whatever really fits into your daily process. So at the end, you should see results that you're used to make some decisions. That's the idea. And as I told you, it is about combining those building blocks into a pipeline. And this complete pipeline from reading in the raw data and until using the model is what we call a template. And I mean, you heard probably the other talks from Navasto. This is a data-driven method, so it can be applied to aerodynamic problems, structural problems, different fields of applications. And usually the pre-processing is the step which needs to be adapted. The rest is the same and can be used as a template. And this is also the structure where we said like, okay, this is the way we want to work. So if you have a look at our training graphical user interface, first step is that you pick a template. We just gave you an example. We have this AIF template where we really said, okay, we have an Alias model of this Autodesk SUV, and we want to make it available in Alias, bringing some engineering insights to the users. So this is a template which we set. We also have other templates for generative AI. You can do your own custom templates. It's flexible. So if you need like additional options, an additional slider, additional input, initial button, you can do this. It's flexible, but at the end, you need to specify a few important things. And the pre-processing basically is, where is the original data lying around? Where do I want to store the pre-processed data? For the training, you need to define what are my inputs and what are my outputs. So just like do it. And I mean, if you have aerodynamic problems, it's probably like a pressure, velocity, drag. If you have like structural problems, it's probably stresses, strains, durabilities. So this is a next template. You can also configure the deep learning model up to a certain degree and submit jobs. So basically, it's how we see it. This should adapt to existing processes, so you can submit those jobs, pre-processing jobs, training jobs, either to like your local workstation under the desk. You can submit it to your in-house GPU cluster. If you would like to do this, you can submit this job to AWS. You can use a queue system, like LSF or Slurm, or run it manually, and then you basically monitor the job. I think if you run an AI model training, since this is an optimization problem, you want to optimize losses. You want to have the losses that compare the real-world solution, the ground truth, with your actual prediction. If you run a forward pass through the network, when you do the comparison, you want the difference between those two things to be as low as possible. This is what the loss describes, so you can have a look at it. It should be as convenient as possible. If you do a pre-processing, obviously you want to look on the reduced shape of the car, that you don't lose information that is valuable for the AI model training, because that's like the worst case scenario, that you cut something off that has actual some information in it. And you also can do predictions in this web app. You can also save those predictions to a file. I think that's completely up to you, whatever gives you like a good idea how to do this. I think time is a bit of the essence. This is why I would like maybe skip the live the live demo of the Alias plugin, but it's as it is in this video. It's not spectacular. If you know Alias, you model something, you open the plugin, hit the predict button, and that's basically it. And what I would like to touch base is what we call a recommendation system. If you remember, like the last question was, if I don't have parameters, how on earth can I perform an optimization? How do I do this? Like it's not possible. And what we came up is that we said like, okay, we would not call it optimization because optimization is a really strong word. It kind of implies that you get one configuration that is really the absolute best. It's the one and only you should use, but that's usually not the case. Usually you have like a lot of stakeholders that have some ideas, have some requirements, communicate some constraints. So what we saw in the last 10 years that you more or less like have what I would call a beneficial region. And you somehow want to find some variants, some designs, some shapes, or some boundary conditions that bring you in this beneficial region where you say like, okay, I'm safe. My part is not going to break, aerodynamic performance is really good, acoustics are great, or at least not, not bad. And this is where we say like, we cannot solve this completely with our technology, but what we can do for you is really recommend a few designs that help you to be in a good range, fulfill your constraints, match your objective function, and stuff like this. And when I talk about this, then I like to describe it that we combine this predictive AI. So we extract the information, we use it for fast predictions, with a generative AI that operates on shapes again. And if you do this, you can automatically test like hundreds of configurations. I think that's the idea. It, at the end, delivers multiple choices to you. And what we heard from all the customers when we started developing this is that if we generate surfaces, the quality of those generated surfaces needs to be high. And we need to stay, they called it like a customer branding. So a BMW should look like a BMW, an SUV should look like an SUV, and not like mix up things, because I mean, that's the old story. If you run an optimization completely free of any shape, the perfect shape is a drop. Maybe if the optimizer is like a bit, I don't know, not well configured, you can also end up with a sheet of paper, but this is no longer a car. Usually you have some constraints also from a design side. That's important. And if you run a quick optimization, the worst scenario is that you run this optimization, it takes ages, and something went wrong, or you're not satisfied with the results. So the idea is, if you do this against an AI model, it's fast, and you can easily say, okay, it was worth the shot, but I want to change the objective function. I need some additional constraints, and I simply want to rerun the optimization again. I think these are some important things, and at the end, again, the basic idea is that we use the knowledge that is inside the company. All the data that is stored somewhere has so much information in terms of which changes in which design state were done in the past. So it was done like in the last generation of the car, for example. Also the impact on aerodynamic, it was done. It was done for different derivatives of the car, former generations, other cars. So this is usually something you can really leverage. And we got the feedback from customers that they say like, yeah, I've done this 5 times. The rear end of the car, the shape of the rear end of the car, I did those investigations like 5 times, and now I'm supposed to do it like the 6th time. There must be something that can help me, that can accelerate this process. I'm not saying I don't want to do some work, but not like all those basic investigations. That's the thing. So again, we combine predictive AI with generative AI, and this is the output of generative AI. So it uses the inspiration from the past, shapes that were delivered by designers, by engineers that were already there in the company, and creates, I would call it, unlimited new iterations. But it does not grow artificial parts. It stays within the customer branding. So we trained just those Autodesk SUVs, so it stays within this, in this realm. You can apply this to global changes. You can also apply local changes if you want. You can also boil this down so that just the mirrors change, if you have any, and not a camera system like here. And with each of those geometries, you get a prediction of the field variables. You can also constrain this movement and say, yeah, I only want to have the rear end moving, front end is like a baseline, should stay the same. And next thing is, if you use those scalar predictions, you can easily couple them to an optimizer. Like, for example, this is a drag optimization. So the drag value is like depicted here on the y-axis, and we did this optimization over roughly 80 iterations. It's like an engineering thing. I think it's a standard approach. But what's not standard is that the turnaround time for such an optimization is roughly 30 minutes. So within the lunch break, this is the story I'm always telling. Within the lunch break, you run an optimization, and when you come back, you have plenty of options. You can look at the results a bit differently because you say like, I'm not only looking at the drag, maybe that's not the only thing that's important. I also want to look at the lift on the rear axis. So I just change the plot and look at the results a bit in a different way. This is something you can do, and then you can say like, okay, let's say I have choices. I just have like the best geometry. That's the green one. It comes with a certain drag. I can trust the prediction, then I'm done. Probably you will never trust the prediction that easily. You say like, okay, I want some additional insurance. I need to perform some simulations, but maybe not on all 80 variants, maybe just on the most promising variants. Those are not the three most promising variants because they look quite the same. I just depicted, in addition to the best green geometry, also the worst geometry in red, and something in between, the yellow one. Just to highlight that with each of those geometries, you get also the results. And then it's really up to you. It just is really a recommendation system or pre-selection system which you don't have to follow. You can just, you have some options, and I just wrote them down. What's your choice? As I said, first thing, trust the prediction. Second, don't trust the prediction. Run a simulation on whatever is valuable for you. Maybe you save some time because you have a pre-selected range of new things. You can also say like, no, I don't take one of those geometries, but I saw like, okay, the front end of the car always looked like this, so I just took a part of it as inspiration for future work and continue. That's also okay. Don't have any hard feelings about this. Or you say, as we discussed, I want to completely rerun the optimization because the objective function was not correct. I had not enough constraints. The outcome is not what I expected, but I know how to do this better. And I have still another 30 minutes until I have the meeting where I need to present next steps, next ideas. Right, and that was my last slide. With this, I thank you very much again for attending this session. And right, if there are any questions, we can do it now. You can also find me at the bar. There's, what was it called, like Bucks and Beers, something like this. And yeah, thank you again. And if there are questions, come to me.